All right. Tesla's big thing is if I take a motor, all right, which is basically a round piece of iron, and I put windings 120 degrees apart from each other spatially. So one here, here, and here on a motor. You create what we call a three-phase motor. And we talked briefly about the benefits of that. I'll talk again about them briefly here. But basically what that means is if you look at a generator, if you look at the terminals of any generator, what you have coming out of it are three voltages that are shifted by 120 degrees, all right, in phase. They have the same amplitude, all right, but they have phases that are different, okay? And so the picture that I would draw for this guy, so this is VAN, VBN, VCN. All right, so if you look at each one, right, the actual time domain voltages, if you looked at them on an oscilloscope, basically they're all cosines, but they're shifted 120 degrees. In other words, their peaks are 120 degrees apart from each other, okay?
Can I ask a question real quick? Real quick.
Yeah.
Why is it 120 degrees? Like, what's special about that?
Well, that's a great question. There's a couple of reasons, which we'll get at in maybe a couple of minutes here as we go through this. You know, what the fact that they're 120 degrees apart is beneficial for at least two reasons. One of them is that it gets the power to be constant, and it also means that the current in this neutral line, this third line down here, is zero. All right, so it has some benefits to it. So we'll talk about that here in a second. That's a good question. All right, are two ways of thinking about this. The fact that I have VAN, VBN, VCN, the voltages in the time domain look like this. And then effectively, if we draw them in the phasor domain, right, what we see is typically this, right? VAN has an angle of 0, VBN has an angle of -120, VCN has an angle of -240, all right? Now, I don't want to go through a lot of the math here. I don't want to get lost in math. I just want to get through the highlights, right? So what we talk about in the real world is either the line to neutral voltage. So I defined these guys the other day, right? I said there's a line to neutral and there's a line to line voltage, right? The line to line voltage would be if I go over here, right? And I do a KVL. So we looked at this circuit, right? And I can do a KVL that goes from A to B through this voltage source VBN, through this voltage source VAN, and I get the VAB is VAN minus VBN, right? Now, if you do that subtraction, VAN minus VBN, all right, if you do that subtraction, then what ends up happening is that you find that the VAB is going to be a little bit bigger than VAN, and it's going to be shifted from VAN, all right? And the discussion we had the other day basically is this, right? So if VAN, VBN, and VCN are as I've drawn right here, right? So I got 0 degrees, -120, -240. What happens is VAB has a magnitude that is the square root of 3 times bigger than the magnitude of the line to neutral voltage. And then there's a 30-degree shift that exists, okay? So what I have here, VAN, VAB, VBC, VCA, so these relationships are the relationships that we basically use, okay? The 120-degree shift between everything is important because of what it's able to do as a result on some of the currents and the power in the system, all right? So I mentioned the other day, if I'm talking in terms of typical power systems, right? So 120 volts RMS is what you have at a wall outlet, right? 120 times the square root of 3 is 208 volts. So when I say 12208, you'll see that sometimes, right? 12208 is what you'll see on a 3-phase load if you look at the label on it, right? And then, like coming into a big building, you know, like Epic or something like we're in here, 277, 480 is pretty typical, right? I have a 480 volt line to line voltage, 277 line to neutral. Okay. All right. Questions about that?
Does that mean there's more voltage in an outlet in Epic than a regular house?
That's okay. Yeah. So what it means is the main service coming into Epic is 480 volts line to line, 277 volts line to neutral. Epic in any big building then has transformers that go from the 480 277 to the 208 120. So the voltage at these outlets is 120, just like it is in your house. But there's going to be a transformer within the building that steps it down to a lower level. Right. Other questions? Okay. All right. All right. So we'll keep going. There's two ways to think about loads, and I actually don't, we're not going to get into this stuff, Y's and deltas. For the most part, I have never in my life had to think about what's the current, you know, or the inside of a delta circuit or something like that, right? So that whole Y delta thing, I don't, or how to convert from Y to delta, you probably saw that in circuits 1. I don't really deal with that problem because I don't think it's a very useful one. All right. I've been doing circuit stuff since 1997, and I don't think I've ever really needed to know that. Right. So the important thing is to know that it exists and it's a thing. Right. So the loads, the important thing here, and I guess this is kind of the main takeaway. When I have a 3-phase load, and I'm gonna jump ahead one of my slides and then kind of jump back for a second. I tried to show this here. All right. What I have in this picture right here, this is, you know, the way I might see a typical motor if I look in a wiring diagram of some sort. All right. So one of the things that's included in this, I took a real wiring diagram where these guys are contactors. All right. It looks like a capacitor to you probably the way it's drawn, but let's not think about that. For a second, what I see here is I've got L1, L2, and L3. So that means line 1, line 2, line 3 coming in. And they hook up to a motor. The motor itself, it says here 480 volts AC. So sometimes people use this VAC to mean RMS voltage. Okay. So the motor, no one thinks about the motor as what's the impedance on a particular circuit of the motor, right? What they talk about is that it's a load, and I think of it as a big lumped load. And so the picture that I have right here, right, where I drew a dashed box around each of the 3 phases, that is the load. All right. If I'm talking about a motor, I don't talk about each individual phase of the motor. I talk about the motor, right? And so that's kind of important in terms of the power. We don't typically talk about each of the individual circuits. We talk about the whole device. All right. We're going to get to some examples of that. But the important thing about this is, what do you notice about the impedances here?
Are all the same.
They are all the same. All right. Now, in reality, that never happens. Right? They're never going to be exactly the same because I can't ever make 2 resistors that have exactly the same value. Right? But they can be really close to each other. All right. Now, when I'm dealing with a motor, they're going to be really, really close to each other in a motor, because the motor is made to be that way. But the load could also be 3 circuits in Epic. All right. So it may be that they're really close to each other, but they're not exactly the same. But for the most part, we deal with what we call balanced 3-phase systems, meaning that all their impedances are the same. Okay. And when they are balanced, that makes the analysis a heck of a lot easier, because what we're going to find is I only need to analyze for one circuit, and then I can very easily figure out what's going on the other 2 circuits, because the answer is just going to be 120 degrees out of phase. Okay. All right. Questions so far?
So if you were actually doing that, even though they're not 100% the same, would you look at them as if they're the same? Or is that a
Well, yeah. So Christian's asking a question. What do you do if there are different? That's a question for a deeper power systems class. You may have heard things like positive sequence, negative sequence, or something like that. There's ways of dealing with those problems, but that's a power systems problem beyond an introductory view of three-phase.
We'll burn that bridge when we get to it.
Yeah, that's a different bridge. Yeah. So if I've got this is typically the way this guy is set up. So in this case, this load can be Y connected or delta connected. All right. From the perspective of, most people, if I get a motor, I don't know if that motor is delta connected or Y connected. If you go to a motor, there's 3 wires coming out of the side of it. Could be a Y, could be a delta, who knows? I don't care, right? We don't think of it like that. So that's how we're going to approach problems here for the most part, is we're going to approach them just thinking of that thing as a box, and we're going to solve it like it's a box. Okay. So if, just to motivate and understand it, this is how we typically start thinking about this. I get a 3-phase load, and I hook up that 3-phase load, VAN, VBN, VCN, like this. VAN hooks up to A, BN hooks up to B, CN hooks up to C, and then I have this guy down here. All right. So this, let's get to maybe the question that was asked earlier about, well, what's good about this 120 degrees? All right. Well, if I do a KCL at this point right here, right, this node. So one thing, this is all a node, right? So what's my KCL at that node? These are phasors, IA, IB, IC, IN. What's my KCL there? Well, yeah. So in terms of the directions, I have IA, IB, IC going into the node and IN going out. So I have IA plus IB plus IC equals IN. Okay. If those voltages are 120 degrees out of phase with each other, and those impedances are all the same, then what's going to happen is basically this. I'm going to have that the currents here, if I look at this guy, they're all going to have the same magnitude. All right, we're going to do a problem here in a second. But this guy is going to have some angle phi I. This guy is going to have the same magnitude. His angle is going to be the same as phase B, but same as phase A, but minus 120 degrees. And current C is going to have the same magnitude as A with an angle minus 240 degrees. If you go through and you take those 3 phasors and you add them up, anybody know what you're going to get? 0. Yeah, that answer is 0. Okay. It's sort of a weird concept, right? Because what it means is I have a current flowing down this wire, a current flowing down this wire, and a current flowing down this wire. But how much current do I have going down this wire? 0. Which at some level should bother you maybe, because current always has to flow in a closed loop, right? So charges have to leave the plus terminal of VAN, go through the load, go through this wire, and then come back and get re-energized through the source, right? I have to have that, right? I have to have a closed loop. What's going on in this case? Is that not happening? Well, yeah, anybody online want to take a stab at that?
I mean, it's happening, but it's at like a pulse almost.
Well, think of superposition happening here, right? So if I looked at VAN by itself, right, the charges coming out of VAN are going through that line and coming back. If I think of VBN by itself, the same thing's happening. VCN by itself, the same thing's happening. When I look at them all together, they're adding up such that the sum here is 0, but there's charges moving, okay? It's just that you don't see it when you look at it, right? Because their summation is 0. But if I look at the superposition, if I look at each of the individual components, right, then it's there. It just so happens that in summation, you don't see it, right? It's a little bit of a weird thought, okay? Now, why does that matter for somebody? Well, there's a couple of reasons why that would matter for somebody. One thing we don't talk a whole lot about, but probably should talk about, maybe it's a good homework problem for the last homework, is when I have, as an engineer, and people ask all the time, what do real engineers do? Well, a common thing a real engineer might be doing is having to size the wire, okay? So you guys should know this, but hopefully you know this, but if I had, as I try to pass more current through a wire, what does that do to the size of the wire that I need?
The bigger the size, the less it burns, right?
The less it burns. Well, you said that's correct. So Zach, what do you mean when you say the less it burns?
Like if it's a small wire and you send a lot of current through it, it's gonna
It
burn
could
the
burn up.
wire.
Yeah, it could burn up, right? So there's a concept called gauge of wire. Hopefully you've heard that term, maybe in physics, right? So wire gauge, as the number of the gauge gets smaller, right? So a 12 gauge wire, like in the lab, you guys use 22 gauge wire, all right? So when you're in the lab hooking stuff up. But you go to, Home Depot and you buy like a, I don't know, a giant shop vac or something like that. That probably has a 12 gauge wire or something like that. 12 gauge is a bigger wire, so its diameter is bigger, right? So Zach, you talked about that in terms of burning up. What's happening to cause heating in a wire? Resistance, right? There's resistance in the wire, so there's I squared R heating that's happening. The fatter I make the wire, what's happening to the resistance? Resistance is
Handle more resistant.
yeah, the resistance is going down as the wire gets fatter. So tell me about the gauge of wire I need for IA versus IN.
IN's 0, right?
IN is 0.
So you can have a
They're really small, right?
I could have a really small wire, right? So effectively, and if you think about it, copper is an expensive resource, right? So effectively what this means is I can, if I do 3-phase like this with 120 degree separation in the voltages, I can basically have these 3 circuits running with half the amount of wire it would have taken for one. All right, it's sort of the idea, right? So that was really kind of what drove it initially. Now I will tell you that's not necessarily how the world works anymore for reasons, again, that are a little bit beyond us, because the currents don't balance as much nowadays. With computers kind of screw this up a little bit. All right, there's some reasons that kind of screw things up, but this is still fundamentally true if I have lights and motors and stuff like that.
If you could, like, if thermodynamics didn't exist and we're in an ideal world, can you run a really big amount of current through a small wire?
If thermodynamics didn't exist,
Like in an ideal
could it?
world, like,
If thermodynamics didn't exist, I could do whatever I wanted to, I guess, at that point. But it's like, if we remade the world, then I guess, yeah, we'll start fresh. But I think what you're getting at, there is a thing or a concept called superconductors, which is to say if I can run temperatures all the way down to absolute 0 or towards absolute 0, I can effectively get to a situation where there's no losses in there, which you can do, right? Or people have gotten close to superconducting at least. But you're taking me off tangent. It's like office hours last night. All right. Okay, so that's the primary reason. The other one, which is probably less clear to you guys, I mentioned this the other day. What is the power? If I looked at the power going into phase A, so I talked about this idea. Power is P of T. That's the rate at which energy is used, right? So that we talked about that early on. If I look at the power as a function of time in a single phase load, what's it look like?
Sinusoidal.
Yeah, it's constant with a sine. It's got a constant plus a sine wave, and the sine wave has a twice the frequency, twice the voltage frequency, right? If I go ahead and I look at P sub A and P sub B and P sub C, if I add those up, this guy becomes constant. That turns out to be a good thing too, all right? And it actually means that my motors become much more efficient, all right? Which at your house, just to give you a sense, at your house, like your air conditioning motor, you know, is a fractional horsepower motor. In other words, it's less than 750 watts. But if I'm talking about a building like Epic, I probably have fans in here that are 100 horsepower, right? So by comparison, that's what, 75,000 watts, right? At that level, I want efficiency, okay? And so three-phase is good in that this constant power gives me greater efficiencies, okay? All right, so those are the key reasons why we use it, but let's get into how we tackle some of these problems. All right, so this is where we ended up on Monday. So if I have, here's a typical circuit. We're not going to do a lot of circuit analysis. We're going to jump more into the power analysis, but I at least think there should be some understanding of what to do here. So if I wanted to solve this problem, all right, how should I approach it? What I want to know is what are IA, IB, and IC? All right. What, anybody want to throw out an approach I want to start with?
KVL loop.
Yeah, do a KVL loop. And in which KVL loop do you want to do, Tone?
I, and IN for the
Yeah.
top.
Yep, the outer loop. Okay, so basically go around this loop around the outside. All right. So if I go around that loop around the outside, I can basically just redraw that circuit for myself. And I can say, well, I'm going to have VAN, and let me draw it exactly the same way. All right, VAN up top. And then I have my impedance. And then I go through the IN loop like that. Okay. The rest of it's still there, right? It's just that I'm just isolating that loop that I'm trying to do my KVL around, okay? And here's IA is the phasor going that way. All right, and this guy is 10 ohms, and this guy is J 10 ohms, like that, okay? So let's say I want to figure out what IA is. Well, this should be pretty easy to do, right? What is IA? What's that going to be?
VAN divided by 10 plus J10.
Yeah, VAN divided by 10 plus J10. All right, so pretty straightforward to try to do that, okay? What would happen then if how would I approach trying to figure out IB?
Do the same concept.
Yeah, I'd do the same concept, right? I would do it around the loop that included this guy, right?
So it's basically the same except VBN.
Yep, that's right. IB would be VBN divided by 10 plus J10. And without even thinking about the loop, tell me what IC is going to be.
VCN over 10 plus J10.
Yep, VCN divided by 10 plus J10. All right, now, without doing any thinking about this, or not too much thinking, what's true about the magnitude of each of those currents?
They're all AA.
Yeah, they're all whatever the magnitude of IA is. That's right. Because the magnitudes of the voltages are all the same. All right. VAN, VBN, VCN all have the same magnitude of voltage. So that means the magnitude of the current in each phase also the same, right? So that's key. Then the question is going to be looking at those three results, right? VAN divided by an impedance, VBN divided by the same impedance, VCN divided by the same impedance. What's going to be true about the angle in each case?
They'll be different and they'll
They'll still be
at a range from each other.
They'll be, yeah. So Zach, I think you said that very close to right. So they're going to be different, but effectively, you know, so it's the magnitude of the voltage is the same in each case, But the only thing that's different about these expressions, these three expressions, is what? It's the angle of the voltage, right? So that means effectively the answer here is going to be this guy's going to have, let's just compute them so we can see it. You tell me, what do you think the angles are going to be?
360 divided by 3,
Yeah, there's be 100.
120 apart.
They're going to be 120 apart, right? They're not going to have the same angles as the voltages, right? Because there's an angle shift that's going on, right? Because of the Ohm's law relationship between current and voltage. But the three phases are each going to be apart by 120 degrees. The currents in each phase are going to be apart by 120 degrees. So what I did, I did that problem. All right. And so here's how I entered this guy in here, right? So when I wanted to figure out those currents, what I did was I said, okay, VAN is 120 times EXPJ0. All right, and then I did this in radians straight away, minus J2 pi over 3 and minus J4 pi over 3. All right, which would be the right angles in radians. And then I said the impedance was this 10 plus J10. And then I calculated IA like this, okay? And I could have calculated IB by doing VBN and like that. What I ultimately get is that their angles are 120 degrees separated from each other. So if I look at this here real quick, all right, and I use this tool here in MATLAB. This is not something I'm going to ask you guys to use, but this thing called Compass, which lets me look at vectors. All right, what I see is that this is IA, this is IB, and this is IC. Now, their magnitudes are each the same, and you can see when you look at this picture that they're 120 degrees separated from each other. Okay. Now, here's a question. Why did I know that this one here is IA?
Because from the equation you got, it would have to be the angle you're subtracting is greater than 0.
Because we have an inductive load, so it's lagging.
Well, both Gideon and Tyler here in the room said correct answers in different ways. So what Gideon said there, right, was that just looking at this, 10 plus J10 is a positive angle. So I got to be subtracting, right, a positive angle. So that means that VAN, if it had an angle of 0, this guy's going to be somewhere a little bit negative, right, which is going to put it in the fourth quadrant. Now, the other thing that Tyler said, which is correct, is this is an inductive load, so it's a lagging load, which means the current lags the voltage, right? So if the voltage is sitting, I think I just have that picture here, right? The voltage is sitting here, right? This is VAN, right? IA is lagging VAN. That's what we defined as lagging, right? And then VBN is over here, and VCN is over here, like that. All right. So the shift between, the angle between them is the angle of the impedance, right? So each of these is the angle of the impedance. Phi sub Z, and this guy is also phi sub Z. All right. So basically, kind of in summary, when I'm approaching these problems, this is what I always find, right? VAN, VBN, and VCN, those are typically our sources. We don't, three-phase systems, power stuff, we don't deal with current sources per se, right? VAN, VBN, and VCN are shifted by 120 degrees. They have the same magnitude. The currents have the same magnitude, and they are also shifted by 120 degrees from each other, but they have a different angle than the voltage. All right, so I wrote phi sub I because it's going to be different than the voltage in general. Now, if I had all resistors, then yeah, the currents, the angles would also be 0, right? But they're not all resistors. Okay. All right, questions there, Kojo?
Is the shift in angle between the voltage and I'm just trying to reinforce the stuff we talked about before. Is that shift the thing that's based off of, like, if it's an inductor?
It is, yeah. The shift in the current here, the question he's asking is, where did that current shift come from? Well, from the fact that there's an impedance, and that impedance is either lagging or leading, inductive or capacitive, right? And that's going to cause that shift. Okay. All right. So, all right, moving on, I guess, to if I talk about three-phase power, which is the main thing I'm going to kind of focus on here, is typically if I have a load, like I said before, I think of that load as a box, right? I don't worry typically about each individual circuit, right? I think about the load as a load. And so if I've got a motor hooked up like this, it's got 3 lines coming in. The implication is that the voltages between those lines are 120 degrees apart from each other, okay, and have the same magnitudes. The thing is, if you look at this motor right here, and if anybody who's ever actually looked at a real motor, if you see it, a motor never has a neutral wire, actually. It always just has 3 lines coming out, right? It has an A, a B, and a C, or as it says here, L1, L2, L3. All right, so there isn't a neutral line. So oftentimes, if I want to measure the line to neutral voltage, it's kind of hard to do it actually, because I don't often have a neutral. So oftentimes, the voltages that we measure are the voltages between the lines. So very often, line-to-line voltage is what's more common to actually see and to talk about. Okay. So bearing that in mind, we're going to try to. So like for instance, when this guy says 480 volts AC. That is a typical line-to-line voltage, right? No one says they have a 277 volt motor. They don't give you the line to neutral voltage. They usually give you the line-to-line voltage. Okay. So all that said, let's say I want to talk about the power in this system. All right. So we analyzed this circuit before with a particular impedance, right? We said initially the problem I did was I said ZY, let's say, it was 10 plus J10. Okay. Like that. All right, let's say I wanted to get the power in the load. So when I talk about the power in the load, that means that I want to get the power in the total load. So what do you think the power in the total load is going to be? And let's talk specifically complex power. What's the complex power in that? How would I get that? All right, well, so V says V times I conjugate. So if I did what V and what I would I use based on the circuit that I've got here on the left side?
Okay.
Could use
We
IA
The
is
superposition.
voltage.
Well, yeah. So I could basically, from superposition, I can get IA, IB, and IC. So, and if I'm talking about one thing to remember, right? If I have 3 loads, this load is kind of 3 loads, right? It's 3 impedances. If I want to get the total power, it's going to be the summation of the 3 powers, right? That's going to be the total power. So it's like a superposition sort of thing, like Gideon said. So what would be the power in each individual phase then? What would that be? How would I compute that? If I wanted to figure out the power in this guy right here, what would it be? What's
every time to reload.
The VRMS squared over the.
well, I could do I could do a couple of different ways, but if I have VAN and IA, how would I do it? Just do what?
Phase voltage times phase current.
Yeah, well, VAN times IA conjugate, right?
Yeah.
In terms of the phasors. And then I would add in VBN times IB conjugate plus VCN times IC conjugate, like that, right? That's how I would get the power into that whole thing. Now, not surprisingly, that's going to simplify itself, all right? And it actually becomes, because if you think about this, right, it's sort of, the 3 impedances are the same. The currents through them are shifted by 120 degrees. So this is going to turn out to simplify itself quite a bit. So let's look at one of those things real quick. Let's say I had VAN times IA conjugate. like that. Okay. So just given what I've got up there, what's that going to do for me? I've got magnitudes and angles. So the magnitude is V, the angle is I, and then what's the angle of that result going to be? What's the angle? So 0 degrees minus phi I. Why minus?
Because the conjugate.
Conjugate.
Conjugate, right? Now if I did VBN times IB conjugate, what's the magnitude of that?
VI
VI. And what's the angle of that?
0.
120
So minus 120 is the angle of the voltage. And then I got
minus
to
VI.
and I got to subtract the angle of IB. So yeah, so it would be plus 120 degrees minus phi sub I. Right? So minus 120 plus 120 became 0. So it's the same, right? So this is 0 minus phi. Well, yeah, 0 minus phi sub I. Let's do VC then. What's that become?
Just 0 minus VI.
Same, yeah. So magnitude VI again, same thing. And the angle, yeah, it's the same. So minus 240, sorry, minus 240. And then I have plus 240 minus phi sub I. So yeah, it's exactly the same thing.
Is that just, that's not like a coincidence, is it?
It's not. Tesla was a pretty smart guy. Yeah. This is what part of what made him so smart was he just kind of sat down and sort of came up with this, right? It's pretty, and what it did was it simplified a lot of things about the way sort of the system was sort of set up. So looking at this, then one way I can talk about the power in this particular system, if I look at, I like I said here, power is equal to the complex power is VAN times IA conjugate plus blah, blah, blah. So each phase. Well, what do we just find from that? How can I write that?
3 times VAN times IA conjugate.
3 times VAN times IA conjugate. All right, so I don't need to do the math separately each time. I can just say it's 3 times whatever I do on any one of them. Okay. So now one thing about what I just did there too, just to be clear, in each of these cases, I said 0 degrees minus phi sub I, 0 degrees minus phi sub I, 0 degrees minus phi sub I. In general, what do we say was the angle of the complex power?
It's always VA, right?
Well, in general, so when we talk about single phase stuff, right? The angle of the complex power is always the same as the angle of what?
Impedance.
Impedance.
Yeah. Phi V minus phi I is the angle of the impedance. And that came from what relationship? Ohm's law, right? The fact that V equals I times Z tells me that phi V minus phi I is equal to phi Z. Okay, so that's really important. And so basically what I can say then is this, right? So in general, the complex power is 3 times VAN times IA conjugate, which is the magnitude is 3 times V times I, right? And the angle is phi V minus phi I, or the angle of the impedance, okay? That's one way to write that. Another way to write that, which is also common, is to say, what's true about the magnitude, so VAN and the magnitude of VAB, what's true about the relationship there? What's the relationship between those magnitudes?
Square root 3.
There's a square root of 3. So, all right, where do I put the square root of 3? So VAB is bigger or smaller than VAN? It's bigger. So I'm going to divide by square root of 3 here. Okay. So if the magnitude of VAN in this case is V, right? So I could also write that S vector as 3 divided by square root of 3 times the magnitude of VAB times I with an angle of phi Z. Okay. What's 3 divided by the square root of 3?
Square root 3.
Square root of 3. I knew Tone would step up with that one, Mr. Cotangent. Okay. All right, so that's my final relationship for that. Is it particularly astounding? Not necessarily, but it's a result that people use a lot. So the way that I think about this, those are my sort of key relationships that I use with these devices. All right, is those kind of two relationships. Maybe kind of summarizing a little bit. All right, when I'm dealing with three-phase loads, just like we had for single phase, I have kind of a key set of summaries, ideas here. So VAN, VBN, VCN, there they are, okay? They have the same magnitude, shifted by 120 degrees. The line-to-line voltages, similar, but square root of 3 bigger, all right? And then these guys are shifted by 30 degrees from their line to neutral partners. The currents, IA, IB, and IC, are all just shifted 120 degrees from each other, okay? And then my complex power basically can be written either like this in terms of the line to neutral voltage, or like this in terms of the line to line voltage, right? And again, this guy is a complex thing. The real part of it is the real power. The imaginary part of it is the reactive power. Same thing as we did before. And typically our way of thinking about it, I don't give a crap whether it's Y or delta, right? Basically what we say is, I have this picture like this. I got a three-phase voltage source, a three-phase line connected to a three-phase load, right? And that's the way we're going to think about it. All right. So we're going to do a problem kind of like what problem 6 is. Problem 5 and 6, which I canceled because I canceled class, they're not going away. They're just due when homework 13 is going to be due. All right. Lucky number 13 is due on Thursday. All right. Because there's no class Friday. So there's no official class Friday. I may still just do like a review. You guys have an exam on Monday, right? Monday the 3rd. So I may just, I'm going to be here. I'm going to be here anyway. So I might just do a review or something. Okay. All right. All right. So let's do this problem. A lot like problem 6. All right. So I'm told that the line to line voltage is 480 volts RMS. Not told anything about the angle, and I don't really care. All right. But I've got the line to line voltage, and I'm told that I got 2 loads. Load 1 is 10 kilowatts at a power factor of 0.85 lagging. Load 2 is 12 kilowatts at a power factor of 0.9 leading. Okay. And I want to know the complex power in each case. Now, one thing that's not totally clear, I haven't drawn a picture of this here, and I didn't in problem 6 either. Okay. One thing about this, I want to look at this in the context of this picture that I have right here on this slide. What's going on there? Yeah. So if I look at this guy, I got my 3-phase source and my 3-phase load. How are these 2 loads? If I have a 480 volt service feeding 2 loads, how would those loads be connected?
Transformer.
Well, no.
Beside each other?
Beside each other. And so once they're beside each other, how so? What does that mean if they'd be beside each other? So here's
Like in parallel?
Parallel. That's exactly what I was looking for. Yeah. All right. So what I have is a 3-phase line that comes out of that source, and they're in parallel with each other. So the way I would think about this is, here's load 1, because this is the way the real grid is set up, right? My house is in parallel with your house, right? You know, everybody is connected. We're all equal, yeah, right? We're all in parallel, right? So load 1, load 2. We all share the same voltage. But different currents. So load 1 and load 2 are in parallel. So the way I would do this, I'd say, well, load 1's hooked up like this. And I'm going to draw this with these little hops, just to try to make it clear that those wires, there's no connection there. Now, those of you guys that get into power, you'll see that typically what happens is people when they deal with these problems in reality, they often draw what we call a one-line diagram, where they try not to show all of these. It gets confusing drawing 3 circuits. All right. This is how these guys would be set up. Okay. 3-phase source, load 1, load 2. All right. Now, knowing that, let's look at the complex power in each load. Okay, so let's do load 1 first. So we're told that guy is 10 kilowatts at a power factor of 0.85 lagging. So going back to our summary from single phase power, if I say I have a lagging load, that tells me something about its impedance, right? So if I have a lagging load, what type of impedance is in that load?
Inductance.
Inductance. All right, I lags V in an inductor. Okay, so in that case, what I have is an inductive load. So this guy's inductive. All right, and what about his compadre here, load 2? He's 0.9 leading, so he's got to be capacitive. He's got to be capacitive, right? All right, so we got that established. So what I want to do is, if I want to get the complex power in each load, what do I need to figure out here? So what do I know? For load 1, I know 10 kilowatts. I know the power factor. So like any of these power problems, every time I start out with them, I said at the very beginning, you're going to be given 2 things, right? So there's 4 things that you could know. P, Q, S, and power factor, right? And you're usually given 2. And then the next step is all trig, right? So in this case, what of those things do I know?
P and PF.
I know P and power factor, right? So if I look at load 1, so for load 1 here, load 1, I know that P is 10 kW, and I know that the power factor is 0.85, okay? So in terms of what that means I know that, okay, here's my 10 kilowatts. And where's the S vector going to be? Do I draw it pointing down or up?
Up.
Up. Yep. It's going to be up. Up because it's a lagging power factor, right? That means my angle is going to be positive. So that means if I want to figure out the angle here, let's call this phi Z1. Let's call this P1 power factor 1. I'll call it that. All right. Phi Z1 is my angle there. Now, how do I figure out that angle?
Cosine inverse. Or
Yeah. Inverse cosine of,
inverse.
yeah, power factor is equal to phi Z1. Okay. Inverse cosine gets me that. Now, if I want to get the complex power, I already know one of the terms in the complex power. I want to figure out the other one here, which is my Q, right? How do I get my Q?
Cosine times.
Tangent inverse?
The P and the
Or
tangent.
just- Do a tangent.
Just P times tangent of the angle.
Yeah, so one way to do this is P times the tangent of that angle. There's a couple of ways to do it. I could say this is the magnitude of S times the cosine of phi Z1, right? There's a couple of ways to do it. But yeah, given what I know right here, right, I can say that the tangent of phi Z1 is equal to Q over P, like that. Right, so Q, and I'll call it Q1, right? So P1 is equal to Q1 times tangent of phi Z1, like that. Okay. Or no, sorry, getting cross-eyed. Q1 is that. Okay. Now, that's how I get that. We'll do the numbers here in a second. What about load 2? All right. How would I approach this load 2? So load 2 is 12 kilowatts, 0.9 power factor leading. What
Just
do I
be
do?
an upside down triangle.
Yeah, same steps, but you would just go in the negative for
Yep,
S.
exactly right. Yeah, it'd be the other way around. So when I look at it this way, so here's 12 kW. This would be my phi Z2 here. This would be my Q, right? Thing I got to remember here in this particular case, right? So P2 is 12 kW. Power factor 2 is positive number, 0.9. But what is, in this case, phi Z2? I can't just say it's the inverse cosine, right? I got to put a negative in there.
Yeah.
Like that. All right. That's my phi Z2. Okay. So I can do the same process. I want to get my Q2. It's a trig problem, right? So Q2 is equal to the magnitude of P2, right? So it's just 12 kW times the tangent of phi Z2. Like that. And there is no need to say magnitude necessarily. No, you're right. Okay, so that's our basic approach to getting that done. That's going to be a negative number, right? Not QZ. This is phi Z2. Okay, same thing here, right? Same basic relationship going on in both cases.
The
Right.
reason it's backwards is because capacitive and inductive, right? Like the triangle.
Yeah, so when I say leading, so the power factor is always a positive number. So if I take the inverse cosine of it, I'm going to get a positive angle, always. The leading or lagging basically tells me whether that angle is supposed to be in the first quadrant or the fourth quadrant. Problem is a cosine of an angle in the fourth quadrant, cosine of an angle in the first quadrant, always positive. So it requires that extra word to tell us, what it is. Okay. All right. So we get that in this particular case. The thing to remind ourselves of here is this is the total power in each of those loads. Okay. So the power in any one phase is what? 1/3 of that. Okay. So that was the relationship we had here. So the power in any one phase is 1/3 of the power that I have in any individual phase. So if I talked about how much power was in one phase of the 10 kilowatt load, it would be 10 divided by 3 kilowatts, right? That's kind of the key relationship I've got going on here. Now, what I want to figure out, so what we just did is we figured out how to get the complex power, okay, in each load. If I wanted to get the total complex power, how would I get that?
What's the S1 plus S2?
S1 plus S2, right? So the total complex power, S, would be S1 plus S2. Just add them up, okay? The other question I asked is, what's the magnitude of the line current from the source? So in other words, what's the magnitude of the currents coming out of here? And what's the magnitude of the current into each of these loads? Now, first of all, if I look at the magnitude of the currents coming out of the source, what do I know about the magnitude of each of those currents?
Yeah, the same.
480 VRMS.
Well, it's the same magnitude, right? And whether it's RMS or a peak, whatever, they're the same value, okay? The magnitude of each current's always the same. And the magnitude of each current going into each individual load is the same, right? The magnitudes going into load 1, the magnitudes going into load 2 might be different, right? But the magnitude of each current into load 1 is the same. The magnitude of each current into load 2 is the same, okay?
I'm sorry, I just want to make sure I heard that right. In each load, it can be different, but
Yeah. So if I have a 10 kilowatt and a 12 kilowatt like this, they're definitely going to be different.
Okay.
But the magnitudes of the currents going into 1 are all the same, and the magnitudes of the currents going into 2 are the same. But the ones going into 1 and 2 are not necessarily the same.
got it.
All right. So if I approach this now, the question is, okay, well, let's look at each individual load. How do I figure that out? How do I figure out the magnitude of the currents into each individual load? What do I know here to help me out with that?
You know P, you know V.
I know, well, I know the complex powers, so I know P, and I know the complex powers in each load.
And V.
What else? What else do I know?
V.
I
RMS.
know V, right? Where is that VLL? That's the line to line, right? So where does that appear circuit-wise here?
From the three-phase source.
From the three-phase.
Yeah, and specifically where from that three-phase source?
From the top.
Between each of the lines.
Between the lines. So basically what it says, if I look at the voltage between here and here, this is 480, right? There's 480 volts between those two things. So I go to my relationships here, right? And so I'm told that the complex power is 3 times VAN times IA conjugate, okay? And it is also these two relationships here. This guy right here is what I'm looking for, okay? Tells me that the complex power going into this three-phase load has a magnitude of square root of 3 times the line to, the line to line voltage, square root of 3 times the line to line voltage magnitude times I, the magnitude of I, and it has an angle of whatever the impedance angle is. Okay, so in this case, if I want to figure that out, let's look at S1. And so let's actually, if I have S1, all right, S1 is equal to P1 plus JQ1, right? Or I can also say it's equal to the magnitude of S1 with an angle phi Z1, okay? So that has to be equal to, using those relationships I just wrote out there, square root of 3 times 480 volts times the magnitude of the current, and the angle of it is phi Z1, right? So how do I figure out the magnitude of the current? So I guess I should call that I1. How do I figure out the magnitude of that current given that relationship?
Magnitude of S divided by square root
Yep.
3.
Magnitude of S1 divided by square root of 3 times 480 is equal to I1, right? The magnitude of I1. You guys follow that?
With the angle of Z1.
No, I don't. Well, but so I'm just looking for magnitudes here, right?
Okay.
Maybe to make that clear, I'll write that in terms of magnitudes like that, so it's clear.
You just solved for I1, okay.
Yeah, right. I don't need to worry about the angles here because I can do the magnitude separately, the angles separately. Remember that one equation is really two equations, right? The angles have to equal on the two sides, and the magnitudes have to equal on the two sides. So if I want to solve that problem now, so what I did was I went to MATLAB here. All right. And I entered in all of my values here. All right. And notice phi Z2, I put the negative sign in. And then to get my currents, right, what I did, I1 mag is S1 mag, right? So that was what we talked about. So S1 mag. So notice how I got the magnitude of S1 is a little bit different than we just did. The magnitude of S1 I said was P1 divided by the power factor, right? Where did I get that from? Well, I got that from the fact that when I drew this triangle, right? This is S1 here. The magnitude of that, right? S1, the magnitude of that line better be P1 times cosine of phi Z1, right? That's our basic definition of cosine that I use to get that. And so I use that to get the magnitude of S1, okay? All right, so, sorry, I wrote that wrong again. P1 is equal to magnitude of S1 times that, right? And then, to answer the rest of these questions, so if I want to do load 2, what would I do? I do the same thing, right? Same thing, but at different magnitudes. And then if I wanted to do it for the current coming out of the source, what would I do? What would I do differently if I wanted to do it for the current coming
Like
out?
one that I choose.
Well, I could add the currents, or the other thing, and this is what I wanted to get this out there, because what I don't see you guys do when you're doing the homework is I can combine the two loads by adding their powers. If I add their powers, I can think of them as one combined load, right? So in other words, I could think of one sort of super load, which is S1 plus S2, right? Connected up to that three-phase source. Like that.
Does that mean I can add everything then together? Or just the complex power? Like,
So powers can always be added up, right? If I want to figure out the total power coming out of the source, I can just add the powers going into each of the loads, right? You could always approach the problem that way. All right. All right. So I'm gonna stop there.